I just want to start off by saying that Tetris is an incredibly addicting game, and I spend like way too many hours in it than I'd actually like to admit. And I can actually see how long I've played, and this is just within the last month alone. So I think I've logged around 12 hours, and that's not including the entire year that I spent playing it before. So you can just imagine how much total time, how many total days I spent of literally just pure game time, where every game is around 2 to 3 minutes. Um, so yeah, it's incredibly addicting, and while it's pretty easy to like understand the game once you start playing. I mean, you're given tetrominoes, which are just all the different ways you can arrange the four minos, and then you pretty much have to stack them to make sure that your game board is clear. So it's really easy to pick up, but it's an incredibly complex game when you dive into it. And so when I say complex, I don't just mean the techniques or the strategies that are being used to, maximize the number of lines you clear or make sure that you can send more lines over to your opponent. But I talk about the complexity of the game itself. So in the same way where we can mathematically understand or categorize games such as chess or Go, we can do the same thing for a game such as Tetris. So the title of the talk, Tetris was Hard, Made Easiest, comes from a paper that was published a couple of years back that was pretty famous called Tetris is Hard, where they proved this big result that they categorized Tetris in a certain complexity class of problem. That paper is around 60 pages long, and it's super, super dense. So not too long after, there was a second paper that came out called Tetris is Hard, Made Easy, where they massively simplify the proof into something like 10 pages. And it's not only just explaining it maybe in in easier terms, they actually reduce the complexity of the proof by not accounting for some special edge cases, which made the original proof super, super long. So this is hopefully an even easier reduction of that second paper. So hopefully it's not just made easy, but made easiest. The goal of the talk, so I want to talk a little bit about just the history of Tetris, because even though it's, I don't know, around 40 years old, it was really messy and complicated in the beginning. And because of that original history, there's a lot of artifacts that we see and a lot of variants of Tetris even today. And then I want to talk about some interesting questions that I had when I started researching this topic, such as, is there a way where you can not lose? So obviously there's no way to win at Tetris. You keep getting pieces until you can't clear your board anymore. But maybe there's a way where you can play indefinitely. Or then I started thinking, well, is there a combination of pieces that you will be forced to lose regardless how you play, no matter how good of a player you are? So there's a lot of interesting proofs that talk about each of these different scenarios. And after that, I want to do a brief introduction into complexity. So if you've never taken a class in computational complexity, this will be a good introduction to what type of proofs you might see, the type of techniques that we'll use to prove these types of things. And then we'll finally go over the actual meat of the proof that categorizes Tetris into one of these classes. And if you have taken a class, maybe you'll see some familiar problems that you probably covered in class, or you'll also see an application of these things you learned to, I think, a problem that's probably more interesting than whatever contrived examples were given in your classes. So to begin, this is the creator of Tetris. His name is Alexei Pajitnov, who was a Soviet computer scientist. And he created the game at the height of the Cold War. So it was 1984, tensions were high, and he was working at the computer center of the Soviet Academy of Sciences. Tetris wasn't actually wasn't his work. It was more of a side passion project because his main field of work was in languages and linguistics. But he did this on the side, and he was so addicted to the game that he created, he would say that, use it as an excuse to say, oh, I was just debugging my program so he can get away with playing it at work. Once his colleagues found out about the game, it instantly took over the entire office. And within a couple of weeks, every single institute in Moscow that had a computer, there was Tetris in that institute. And it actually got so bad that some departments had to ban the game outright because people were no longer working. They were just playing the game all day long. And if you think about the Soviet Union, where productivity is like the thing that everyone should strive for, now everyone's no longer working because they're playing a video game. That was just super antithetical to the Soviet Union's values. So it didn't take long for his bosses and the department to be not very happy with the success of the game, because the Soviet Academy of Sciences was a very serious place to do research, and yet their big export to other centers was, oh, this video game that forced everyone to not do any work. So they weren't very happy with the initial success of the game. Now, another key thing to note is that there were no intellectual property rights in the Soviet Union. So once he created this game, he didn't actually own it. It wasn't his property. It was the property of the center or of the government. So he couldn't actually sell this game or capitalize on it or even export it, even if he wanted to. And even if there was a way, that the idea that, oh, the Soviet Union would export a video game to the Western world to play was, especially at the height of the Cold War, was not something that would happen. What made this really difficult is when there was a man by the name of Robert Stein, who was a software salesman for a London-based firm. So he saw this game when he was at a conference, and he wanted to get a slice of the action. And he tried to negotiate the rights to this game, and he ended up selling the rights to a game that he didn't yet own. And this was due to some miscommunication between him and the department itself. And this made it incredibly messy. Within a couple of years, there were multiple companies laying claim to the game, producing their own versions of it, when Pajitnov had none of the cut, and he missed out on millions of games being sold without actually cashing in on any of it. The story does have a happy ending. Within many years later, Pajitnov did reclaim rights to the game, and now he is a owner of the Tetris company. But he missed out on a lot of the initial success. What's interesting to note, though, is because there were so many different companies that were creating Tetris, there's a lot of subtle variations of the game. And so we'll actually have to take that into account when we go over the proof, because there's some ways that you can place the pieces on the screen that are different within versions. So for example, obviously in Tetris you can rotate pieces by 9 degrees and you can translate them anywhere you want on the board. But what happens if you're right at a wall and you try to rotate a piece? So some games will say, well, you can't do that because your piece will extend beyond the wall, so it'll prevent you from doing that. However, some games will say, well, it's fine, we'll just push your piece over a little bit to the side. And that actually changes your gameplay depending on which version you play. So that's important to take note of. Okay, so one of the questions I originally had was, is there a way where you can not lose a Tetris, right? You can obviously not win, but is there a way where you can play forever? And so there are proofs that say, for a certain set of restrictions, for these three in fact, you can play forever. So if you can see, like, the tiling on the right-hand side over here kind of shows the pattern that will allow you to play forever. So you can see that there's certain things that repeat, and you can pretty much tile this indefinitely, and you'll continue to clear rows. Now the restrictions, there are 3 of them that actually make this possible. The first is a random generator. So there's also different ways of generating the pieces for you to play in the game. What a random generator does is you have a bag, which consists of the 7 tetrominoes that exist. And once it generates those 7 in some sequence, it will give them out in order to you until you use all of them. Once you use all of the 7, it will generate a new bag, and then continue to deal those out. And that goes on indefinitely. So you will always use one of the 7 will not repeat, unless you were lucky enough where the last piece of one bag is the same as the first piece of the second one. So you can only really have 2 pieces that are the same in a row with this generator. The second restriction is that you have a hold feature enabled. So this allows you to not place a piece down, but to have it in a temporary store, which can only hold 1 piece. And it will make a little more sense when we see an animation of someone actually using this tiling in person to continue the game. And you have to be able to see the next 3 pieces. So that allows you to vary where you're going to put the piece, because you can see slightly into the future. And these 3 are not actually that uncommon to see in real games. Like if you were to play many different versions, these are probably going to be available. And in fact, the version that I showed you in the beginning, the one that I logged 12 hours, it allows you, it has all of these enabled. So it's a little fast, but you can see that the pattern is really similar to the tiling that is on the right. You can see that we have this repeating pattern right here. We have a well in the center, and we also have a different tiling on the other side that consists of the red, green, and purple pieces. And just to make it a little bit easier, there's special names that are given to these pieces. So I'll be referring them instead of the square one. I'll say that the square one, the yellow one, is called an O piece. The orange one is an L piece. The blue is a J piece. Cyan is I. This purple one is T. Green is S, and red is Z. And I know it's a lot to remember, but you can kind of see the letters when you look at it. And that'll just make talking about these tetrominoes a lot easier. Okay, so we know that we can play forever without tiling, but maybe there's other ways. What if we had a special version of Tetris where we didn't have those 7 bags, but we only had 1 piece, or perhaps two pieces? So there is a theorem that says that we can't have single-piece winning strategies for all tetrominoes. This pretty much means that if you were given 1 piece on repeat, if you had only T pieces or only square pieces, you can tile the entire board and you can eventually play forever. And the way that you would go about proving this is you would say, one way is how Bertowski did it. He showed a state diagram showing the order of the pieces as they continue to fall and how you would be able to clear every single row. And this way you could play forever. So it's not too hard to see this for other pieces too. So for example, square pieces, you would just continue tiling them until they clear all the rows. Same thing with the eye pieces, the tall, long ones. You could also just continue to stack them. And it will get a little bit more involved when you deal with others, but it's not too bad. So for this state machine, we're dealing with the L piece, the orange piece. You can imagine that we start over here, and each of these are states. So this represents the state of the board with each piece drop. To move from one state to the next, it's represented by this transition, which pretty much tells you that you're adding a new piece to the game board. So we start here, we can see that we tile these L's from left-hand side going to the right-hand side. So we continue to put 1 down, we put the second, the third. And just as a note, the width of this, usually in Tetris, is 10 columns wide, and it's usually 20 rows high. So you continue to put these down until you get to this pattern, and at this drop, you clear this entire row. So you cleared the last line. And now you rotate the pieces and fill them out from the other way. And you can see that you pretty much, when you do this, you'll end up clearing the whole board. A question for you guys is there another, using rotations and translations for the L piece, is there another type of, I guess, proof that you can think of that will clear this board that isn't this one? So in other words, what's another way of tiling these L's so you can always clear? Yeah?
Okay, so you have the regular L,
Mm-hmm.
you put it down, then could you put it like 180, completely upside down, and then just put it like directly on top?
You mean like right here?
Yeah, like on top so that it goes like...
Yeah, exactly. That's exactly what I had in mind too.
Okay, cool.
Yeah, which would pretty much get you to, if you cut this part out, you'll have something that's 2 by 3, right? And then you can continue, it'll end up looking like this anyway. So yeah, that's another way. Mm-hmm.
Is it like putting the tetrominoes together to fill up the bottom 3 rows, like making a larger prototype, the smaller?
So I don't have the exact definition of prototile, but I think that's the smallest type of tile that you can have. So I don't think that 2 by 3 would be a prototile, but it would be, you're just combining the two to make a larger piece, I guess.
But that piece would fill the bottom 3 rows, right?
Yes, it would fit the bottom 3 rows. So you would have to do that, you have to do that 5 times, because each one is 2 columns wide. So you do 2 times 5 and you fill the entire. So you'd have 5 of those repeating patterns. So you can draw an equivalent state diagram that kind of shows the same thing. I don't know if that answered your question, Morris. Okay. Does anyone have any other questions so far? Okay, great. So for one-piece variations, it's fairly straightforward, and you can take a look at Bertowski's other proofs if you really so like how he tiles for the rest of the 6 pieces. But we can prove something a little more interesting too. We can say, okay, well, instead of just 1 piece, what if we had 2? And more specifically, what if we had a game that could only have the square and either the J, L, or the I piece? And so there's a theorem that says that if we only use these 2 pieces, the square and one of those 3, we'll also have a winning strategy. So we can continue to play forever. And this proof is a little bit more involved than the other one, but it follows a somewhat similar thing. We'll have to split it up into 2 cases. One where we get a square, and one where we get the other, one of the 3s. So for the sake of the example, let's say we're also dealing with L's, because we've seen that before. So this is kind of the algorithm of how you would play this to have a winning strategy. If you have a square piece, actually, sorry, before I go into that, we have to define what a bumpy lane is. And it's, what that pretty much is you take the playing field and you divide it into lanes of 2 columns. So you will have 5 lanes on the board. And those 2 columns have to be adjacent. If those columns have different height, we will call them bumpy, and if they have the same height, we will say they're not bumpy. So if we have a square piece that we put down, because it takes up 2 by 2, that would be filling a lane. And of course, the square is of equal height, so that would say it's a bumpy lane. If we just had an L piece that we put down, they're obviously going to be of different heights, so we'll say that it's bumpy. So if we have a square piece, we say we play the square piece in the lowest smooth lane, unless there's a bumpy lane with a height of at least 2 less than the other lanes. So we put down the square if it's, unless there is a bumpy lane, in which case we put the square in the bumpy lane. And then for the non-square piece, if there is a bumpy lane, we play the non-square piece to smooth it, but if there isn't, we'll put it down to make it bumpy. So I know it's somewhat confusing, but we can take a look at a visualization that shows what's going on. So for example, we start off with the square piece. We're kind of starting a little bit into the game, so don't worry that there's 2 here. Pretend that we only had the square. Okay, we have a square, we put it, there's no bumpy lane, so we put it in the lowest smooth lane. Now we have a non-square piece, and there is no bumpy lane, so we put it down to make it bumpy. Does anyone want to take a shot on guessing what this next piece, this next L, where that would go according to this algorithm? And it's okay to take a second to make sense of it. So the question is, if you have an L piece, where would we put it according to this algorithm? Yeah, go ahead.
Which you took what Mia suggested a few slides back.
Exactly, that's exactly it. You would rotate it and you would make it non-smooth. Okay, and then we know that, so you put this L piece here, and then does anyone want to take a guess on where the square piece would go after?
So you asked why putting the L piece there makes it not smooth.
Right, so remember that every lane is defined as being 2 columns wide. So these two, the one that the square fills, is going to be a lane. And because the height of these 2 columns within the lane are equal, we say it's smooth. But this one, for example, these 2 columns that make up a lane, the heights are, they're different. This one has height 3 and this one has height 1. So we say that this lane is bumpy.
But once we add the next L upside down, won't that column have the same height in those 2 squares?
Yes, well, you're saying that these will have the same height?
Yeah, so it becomes smooth.
Exactly, right. Yeah, that's exactly what's going on. And that's the point, right? So when we have a non-square piece and there is a bumpy lane, we play it to smooth the lane. So you're exactly right, we would just be smoothing it. Sorry, yeah. Did anyone want to take a stab at where you would put the square after this point? Yeah.
On top of the square that's already there?
I think not quite, because it says that you would put it in the lowest smooth lane. So by lowest, you would say that it has, in this case, it would have height 0. So this one would have height 2, so you would actually just put it here because this obviously has no. So yeah, we can continue, and we can kind of play and see what it would look like here, right? So we put it there, then there, and we can continue doing this, and you'll see that we can actually continue to clear these rows, regardless of the order that we get these squares and L pieces. Yeah. Does anyone have any questions before we move on? Okay, sweet. So not every piece sequence can have you win. So we've seen some for single piece variations or ones where you have a square piece and an LJ or an I. However, there are piece sequences that have been proven that will make you die. So no matter how you play, no matter how good of a player you are, you're always going to lose. And so there's a theorem that says that a Tetris game consisting of an alternating sequence of these green and red pieces, the S and the Z's, it will always end before 70,000 pieces have been played. Now, 70,000 sounds like a huge number, so you think, oh, you can probably play for a super long time and it only comes up eventually. The thing is, this 70,000 number is an upper bound, and it's not the least upper bound. So very well likely, we can continue to prove that the upper bound is actually much less. And I think it's been statistically shown that you will die somewhere around 2,000 pieces in, even if you're played perfectly. So there's a video here that kind of has, it's literally a video for 9 minutes long. It has like 1,000 views. But it's somebody playing the S and the Z sequences until they're forced to die. And you can maybe, theorize that, okay, well, we see that we're getting these columns that we can't clear with these pieces until they pretty much fill the entire board. And at that point, you can't continue playing. So not every piece sequence will allow you to win. And I think there's, I would guess that there's probably a lot more that would make you die than there are that would have you win. Okay, so there's some further questions of this. So are Are there other p sequences that will force a game to end besides the s and the z's? I think there might be another one, but there's not too many that have been found. And for example, what if we, instead of play with tetrominoes, we play with pentominoes? So those are pieces that have 5 minos. So there's a lot more shapes that you can make instead of 7 shapes with tetrominoes. I honestly I don't even know. I know it's larger. And if you take a look at the shapes, they're much more awkward looking and they're much harder to tile. There's versions of Tetris that are with pentominoes. I think it's like, yeah, I don't remember the name of the games, but they're much more annoying to play in my opinion because they're just so much harder. So even if we were to find strategies, there's another strategy that was found for I pieces and JNL, but they require over 100 state diagrams to check. So the one that we saw before, that's just one. Imagine having 100 different ones just to prove for a piece sequence that relatively looks simple. And this is an indication that Tetris as a problem is computationally very difficult. And it's very, even for the first question, it's very hard to find a piece sequence that will force the game to end. And so this is where I want to jump into kind of introducing you to what computational complexity is, and is there a way that we can actually categorize in what class is Tetris, does Tetris belong in? And maybe that can tell us why these problems are so difficult. So you might have heard of the classes P and NP, and there's a big open problem in computer science about these two classes. And in fact, it's so famous that the Clay Institute of Math will award you $1 million if you were to solve it. So granted, it's been around for many decades, and there hasn't been, it seems like no one's really gotten to the heart of it. And in fact, there's a lot more proofs that show that we don't even know how to solve such a thing, rather than proofs that show anything about P and NP at all. So we know more about how we can't do it than about how we can, which I think is kind of funny. So maybe we won't even see an answer to this question, but the prize is still out there. Before we go into the classes P and NP, they pertain themselves to something called a decision problem. And it's very simple. It pretty much is just a question that has a yes or no answer. So an example of a decision problem would be, if we have an array, can we find the largest element in that array? Another decision problem could be, if I were to write, this is another famous problem called the halting problem, where if I wrote some random computer program, and if I were just to look at the program, could I know if it's going to run forever or if it's going to stop eventually? And so that actually is impossible to decide. But it's still a problem, decision problem nonetheless. So the class P is just a set that contains all these decision problems that can be solved by a deterministic Turing machine using a polynomial amount of computation time. All that really means, without going to the definition of what a Turing machine is that we can have a computer solve this problem relatively quickly. That's all that it's saying. So we know how to solve these problems in a relatively efficient amount of time. So for example, if we have this question, can we find the largest element in an array? We can. And I mean, can someone give me a really naive algorithm for how we would go around doing this? If we have an array, how do we find what the largest element in that array is? Yeah.
Go through each element and keep track of the largest one we've seen so far.
Exactly. And we know that we have to eventually check every single element. So we're going to have to check as long as the array is big. So if we say the array is n long, it's going to take O of n time. But that's relatively still fast. And even if we have things that are n squared or n cubed or n to the 20th, we look at these things as they get really, really big, as n gets huge. So that's still, we call that relatively efficient. And you can see here a graph of different complexities. So our problem that we saw before follows O of n. So as n gets big, the computation scales, the time that it takes to solve this scales linearly. Things like n factorial or exponentials like 2 to the n, those just blow up insanely quickly. And it's not even, it's not feasible to solve such an issue. So there are some problems such as, maybe you guys have heard of the traveling salesman problem. And the point of the problem is, imagine you have a salesman that's trying to sell snake oil to the entire United States. And he's kind of cheap, and he wants to take the shortest trip possible between all the cities that he wants to visit. How could he tell what the shortest path between all the cities that he has to visit is? The tricky thing is, it's actually not possible to know what the shortest path is unless you were to try out every single combination and permutation of the cities. That would take finding those combinations is n factorial. So even if you have something like 5 cities, you can more or less do it. That's 120 things to check. But if you have like 20, which isn't too outrageous for if you're trying to visit a lot of cities in the US, it becomes very, very difficult to solve. So that is a problem that would not be in the class P because we can't solve it in a polynomial amount of time. It would take much, much more. So that's the class P. Then we also have the class NP. So NP is also a set similar to the class P, and it's also a set of decision problems. But these are things that we're no longer interested in solving. These are things that we're interested in checking. So if we have a problem instance, so we found an instance of the problem, so if we are given an array, for example, in the previous example, and we know that the answer is yes, we can tell that we can verify that solution in a polynomial amount of time. So even if we can't solve it, we can check it relatively quickly. And the key here is the word instance. So when I talk about that, I mean, it's not the problem as a whole, but maybe we're given, it's not like any array, but we're given an array, and we are given an instance of it, and we have to check it. So when we're given something, and we know that we can verify it, we call that a proof or a certificate. So here's an example of an NP problem. This is called the subset sum problem. It's kind of a tongue twister. And we'll see another problem down the line that's really similar to this one. So this problem is pretty simple. All it's saying is, if we're given a set of integers, can we find a subset within it whose elements sum to 0? And if we're given this, -7, -3, -2, 5, and 8, it's pretty clear that we can. It's just those three. So in this case, we're given this subset. So this would be our proof. And we can verify it efficiently to see if the sum is to 0. So I guess I kind of gave it away in the slide, but what would be the actual algorithm that we would use to check an instance of this problem? So if we're given a set, what would be the things that you would do to check if this subset works or if it doesn't work? Yeah, Mia?
You could sum up all the elements in the certificate, and then you would get like a yes or no answer.
That's exactly right. So it's just summing integers, and we know that we can do that relatively quickly. So the algorithm is just we're summing numbers up, and we know we can do that in polynomial time. So that's enough for us to say that, okay, the subset sum problem is within the class NP. So already we kind of have a small, proof, or so to say, that we can categorize this problem within a complexity class. So we already did that. And we have this third class. I know it's really getting definition heavy, but this is the last one. It's the definition NP complete. And this is just saying that we can reduce another problem in NP to this problem X. So NP complete is the set of all problems X in NP, but we can reduce any other problem to the one that we're given. And if we can find something that reduces to it, we can say that it's NP complete. Intuitively, that just means that if we can solve a problem Y quickly, and we're given X, then we will know how to solve X relatively quickly as well. This graph is kind of the two opposing thoughts of the P and NP question that I brought up earlier. This is the thing that you can get $1 million for if you were to show it. We just have no idea if the set P is equivalent to NP or if they're not. And so these are the two different flavors, and most scientists think that we're somewhere over here. Most people think that they're not equal, but we don't really know for sure. So, but if you were to look at this, I would say to pay attention to the left-hand side. Yeah, so you can see P, NP, and NP complete, and where their intersections are, and kind of an understanding of their complexity too, because we know that P is relatively easy to solve and check, but NP complete problems, you can't solve them quickly, but you can check them quickly. So it's higher up because it's a harder problem. Okay, last definition, I promise. This is just to formalize what it means to reduce something. And the reason I'm bringing all this up is because our big result at the end of the talk is going to be showing that Tetris, the game, is NP complete. So the reason we're bringing up reductions is because we want to be able to reduce some problem that we know is NP complete to Tetris. And if we can do that, if we know that we can solve, if we can check some other problem relatively quickly, then we can also check Tetris relatively quickly. So we the type of technique that we use to show these types of things is called a mapping reduction. And all it is just an algorithm that can transform an instance of one decision problem into an instance of another decision problem. So this is, think of it maybe such as like, if you're given the task of lighting a fire or making a bonfire, you can simplify that by saying, okay, I need to light a box of matches. So if you can reduce the problem of making a bonfire to lighting a box of matches, and you can show that you can light a box of matches relatively quickly, you can also light a bonfire relatively quickly. So intuitively, that's just kind of what we're doing. We're simplifying one problem to something else. And it has to satisfy this thing called the answer correspondence property. All it pretty much means is that because, oh yeah, sorry, go ahead.
It's actually about this bit, so it should be.
Oh, it's about the, okay. Yeah, the property pretty much shows that if we were to do a reduction, we know that an answer to one of the instances of the problems will also map to the other one. So if the answer to this problem is yes, then the answer to the reduced problem is also going to be yes. And if the answer to the original problem is no, then the answer to the reduced problem will also be no. So that kind of shows you that we're like mapping something we're mapping from one problem to another, and those its properties have to carry over, and that's why it's actually meaningful, because we know that the answer will stay the same. I don't know, yeah, go ahead.
So the answer staying the same just means whether there is an answer or not, or in what time, not the actual solution to the problem.
Well, not the solution. It would be like if we have in the example of the bonfire, like if we know that we can't light a bonfire, we don't know how to do that, and we reduce that problem to lighting a box of matches, then we also know that we can't light a box of matches since we can't light a bonfire. But if we can, then we can light a box of matches. I don't know if that, I didn't totally understand your question. I don't know if that answers
it. No,
it.
that makes sense. I was just thinking of problems where the answer isn't just yes or no, but we are just talking about.
We are just talking about decision problems. Yeah, so it is limited to questions that have a yes or no answer. Does anyone have any other questions about this or anything before? Because I went through a lot of definitions, and this really made my head hurt when I was researching it. So I totally understand if I'm giving you a headache as well. Yeah.
So is it, I took number theory and cryptography, is it sort of like when we reduce problems like the discrete log problem to show that it can't be solved in like a certain amount of, or like efficiently? Is that not about decision problems? That's something different?
Well, I'm not too familiar with it. I don't know if what you're talking about is more like a bound for a problem. So in the same way that we know we can't do it quickly, or like we found a bound, it would take this amount of time, and that's infeasible. That's not quite what we're saying here, because I guess this is just a level up. It's not really an upper bound, but it's a more abstract way of saying that. What are you talking about, reductions? Or?
Yeah, I guess I was trying to figure it out.
Yeah, it's kind of confusing, but this one is pretty much saying that we can kind of tie two problems together. And if we know that it's, if we can take something and make it simpler and say something about that, we can say something about a larger piece.
Okay. So it's not necessarily about feasibility.
Right. Well, it's when we talk about something that's efficient, we just say that it takes a polynomial amount of time.
Okay.
It could still be huge, right? It could be n to the 100 power, but it's still polynomial, so we say it's good enough because it's just so much less than n factorial or other types of complexities. Okay, great. Let's move on. So that was a really boring and definition heavy, but we kind of need to understand these things to be able to prove this big result that Tetris is NP-complete. It's within this class. It's a hard problem to solve, but it's relatively easy to check. To do that, we're going to perform a reduction between a problem that we know is NP-complete and Tetris itself. And the problem that we're going to choose is called the three-partition problem. And it's somewhat similar to the subset sum problem I showed you earlier. All that three-partition, I'm going to just call it 3-pat. All that it's saying is that if we're given a set S of positive integers, can we partition S into disjoint subsets of size 3, where the sum of each is to some number t. So I know it's a mouthful. All that's saying is we have a set S, and we know that we can partition this into equal sets of size 3, because there's 6 elements, and that's divisible by 3. We know that this bigger set can be partitioned into these two disjoint sets, 159 and 267. And so given this instance of the three-partition problem, we can verify that we can do that, right? And here's exactly how we would do that. One important restriction that we're going to need, and actually, sorry, so just to clarify that, In this case, m would be 2, right, because we have 3 times 2. So the cardinality, the size of S is going to be 6. And the sum of each partition, or what we would call T, is going to be, what is that? It's going to be 15. So in this case, we have size 6, and T is going to be 15. And we can relatively easily check that both of those things hold. One restriction that we need is that every integer has to be between T over 4 and T over 2. So 15 divided by 4 and 15 divided by 2. And we'll see a little bit later why we need that to make our proof work for Tetris. But that's really just the 3-partition problem. And what the amazing thing that the authors of Tetris is Hard did is they took this problem and said, well, given any instance of this, we can map that out to a game of Tetris. And so we can show that any solution for this problem will also clear all the rows of Tetris. And if this doesn't work, then we can't clear the Tetris board. Yeah?
Right, so this example doesn't satisfy that restriction, right?
This one doesn't, you're right. The thing is there's different variants on the 3-partition problem, and the complexity of each of them is equivalent. And I just use this one for the sake of example because it'd be, like I didn't want anything numbers that were too big. But you're right. But this is a restriction we're going to have to keep in mind for the later parts of the proof. But yeah, thank you for pointing that out. Are there any other questions about this part? Okay, great. So we can actually get into the whole heart of the matter and prove that Tetris is an NP-complete problem. So we need to know something about 3-pat. And it was proved that it's NP-complete. And it was proved by Gary and Johnson. And it's like notoriously complicated. It's super long. People in papers say, like, I'm not even going to try to sketch a proof out because it's just so annoying. So someone else did that work for us. We can just use this result to reduce other problems from it to say something about Tetris, for example. So we're just going to need to know that 3-pat is NP-complete to show that Tetris is as well. Okay, so now we have to formally define, like, what is the Tetris problem, right? Because you might have different goals in Tetris. You might want to clear the most number of lines or send the most number of lines to your opponent. We're just trying to say, can we clear a whole game board? So if we're given a game board, that doesn't necessarily have to be empty. There could be pieces in it, right? There could be junk on the board already. So if we're given a game board, and we know what our finite sequence of tetrominoes is going to be, can these pieces be rotated and translated and put in the places they need to be so that the last piece fills the entire board game? So that's the Tetris problem. You can think that, wow, this looks really hard to solve. Like, we found, 2 examples, right, where we have the L pieces being put together to fill the game board. But it's hard to check if we're given some arbitrary sequence and arbitrary, or it's hard to find one of those, but we can check them fairly easily. We can just put everything down and see, does it actually work out or not? So the game plan, this is probably the most important thing for this entire proof, is to understand that we're reducing 3-pat to this problem Tetris. So what we're trying to say is, how can we create a game board and a sequence of pieces such that if the 3-partition problem, the answer to that is yes, Tetris will also result in a yes. And if an instance of the 3-partition problem is no, then Tetris is going to result in a no. So for example, if we have this set of numbers, can we create a game board and a sequence of pieces so that if this answer is yes, we can clear the Tetris board. And if this doesn't work, then Tetris, we can't clear the board. That's effectively what we're doing. So the whole meat of this is we have to construct a game board and a sequence and then show that that the answer correspondence property holds. That's how we're going to do the reduction, and that's kind of the whole meat of the proof. So this is probably the most important part to understand because it's it's really the big idea. Like, there's a lot of small details, and it's not, you can kind of hand wave them off a little bit, but this is really what we're doing here. So are there any questions about what's going on? Like, why are we even creating a game board or anything about that? Okay, and I think it'll make more sense as we kind of go into the proof and we see how that works. So they did the work for us, right? Like, we can see that they created a game board. And there's a couple unique things about it. So we can see that there's different buckets, right? And within every single bucket, there's a number of notches. There's also a lock up there, and there's a fill area on the right-hand side. So what this game board will do is it kind of represents the structure of a 3-partition problem. Every single bucket is going to be a subset. So in the last example where we had those 2 subsets, each of these buckets is going to be one of those sets. And every single like combination of notches is going to be a value. So what we're pretty much trying to do is, like, if you're given some number, we're going to be filling these notches up. And once we get to the end of that small subset, we should be able to fill the bucket. And that's how we're reducing that original game, or a 3-partition, to Tetris. Now you might be thinking, okay, like, why that more or less makes sense. Okay, I'll believe you, but why do we have this lock thing, and why do we have this fill area over here? That looks really awkward. The reason we have that is because we don't want to clear any lines until all the buckets are filled. So that's really important. We don't want to clear any rows before we fill every single one of the buckets, because we want to, intuitively, we want to, like, fill every single set without deleting elements from it. So the reason we have this lock is because we have this fill area on the right-hand side here. Even if we were to, like, put stuff in correctly or fill stuff up, we can't clear a line because this space is empty. And we can only get to it until we fill all the buckets. We put the lock piece in to clear the top 2 rows, and now we can deal with the fill area. So this requires you to do the filling, and then you can clear. Some important things about this is, what is W, R, and H? So H is the space that you have to fill, and R is going to be just some kind of number of rows that allows the player enough time to rotate and translate their pieces and put them wherever they want on the screen. We're kind of, like, waiting past it. It's somewhat of an assumption, because if you were to play a real game, it's not always likely that you're going to be able to put the piece wherever you want. Actually, in NES Tetris, there's a certain point where the game gets really, really fast. And there's a limit to how fast you can press the button to move it across the screen. So there's actually points where you have so much junk on your screen and you're trying to put pieces that even if you had a long bar on the left-hand side and you're trying to put it on the right, like, you literally can't. So you have to do something else to win. There's a lot of, people are still really actively playing the game. And there's a lot of techniques even now being developed, like physical techniques, like how to play in the controller to move pieces faster across the screen. One of those is called rolling. So what that happens is it's actually really slow if you have a controller, to mash one button. You can, like, use different fingers or whatever, but it's going to be kind of slow. They realize that it's faster to actually hit the controller from underneath into your finger. So you put the button into your finger instead of your finger hitting the button. And so they use, like, 3 fingers to roll the controller from the bottom to increase the number of pieces that you can put down. So there's, like, a lot of work that goes into trying, but we're going to say, forget about that. We'll assume that we can put pieces wherever we want. And W is just the width of the game board. Also, what's important is that there are T plus 3 notches in each one of the buckets. So that pretty much means that there are, so for example, if the sum in the last problem was 15, we'll know there's 15 plus 3 notches in each one of these buckets. And we'll see why we need that in a little bit. Are there any questions so far on what this means, or just a reminder of what the notches were, what the buckets were, what represented what? Because I know it's kind of a lot that I'm throwing at you. Yeah.
So isn't the normal Tetris board W equals 10? So, like, isn't that just like a special instance for this?
Yeah. So I think W is defined to be 4S plus 6, and S is the number of buckets. So if you set S to be 1, you can have a game board that's 10Y. So yeah, you can. I think this is more abstracted. It's a more general case, but you could make this work for an actual game board, which is why it's still relevant. Yeah. It's a really good question. I had the same question myself when I was reading through it. So, okay, we constructed, remember back to our game plan, right? We have kind of 2 things to do. We have to create the game board, and we have to create a sequence of pieces. So we just made the game board, and we'll see that that works. Now we have to create a sequence of pieces that will make the 2 actually work out. And so they came up with this algorithm. What you have to do is, there's 4 steps. So each one of these algorithms get at least the first 2 steps. Actually, my bad. The first step gets carried out for every single value. So when we have those disjoint subsets, where we have 3 numbers, each one of those numbers is going to be a repetition of 1. Once we get through that 1 subset, we're going to go to 2. And we continue this until we fill all the buckets. Then we put the lock in, and then we fill that area up. So I know it's hard to grasp without actually seeing it. So we'll take a look at a walkthrough of a trivial example where we have a subset 1, 1, 1, and we say that T is going to be equal to 3. And so we'll see how, okay, first we put the begin piece in, then square, then a j piece, square, square, j piece, square, and then we followed up with that. You'll get a sense of how this works when it's played. So it's a little fast. So there's the begin piece. These three are one, then we end it. So the begin, three piece, and then the ending piece. And I'm just scrolling up to continue to see the bucket because it's really tall. We can see the lock on the right-hand side. We do one more iteration, right, because t equals 3. We end it, put the lock in, and now we start clearing the whole thing. So you just showed that for this subset, right, we showed that this algorithm and this initial game state board, we were able to clear it. So we were able to kind of map a yes instance of the 3-partition problem into a yes instance of the game board that we created. So this is a yes instance reduction actually working. Does that make sense? I can leave it up on the screen just to watch it again because I think it's kind of cool. And it also takes a little bit to kind of wrap your head around. Sweet. Okay, so yeah, we can see just another example of it's effectively the same thing, but instead of a being 1, we have a equals 3. So in this case, we start with the begin, and then because a is 3, these 3 pieces, the square, L, or the square, j, and the square, happen 3 times, right? So 1, 2, 3, then we end it. And then we go on to the next element in the subset. So the reason in this other example we had 1, 1, 1, so we only had a, oh, I guess I realized I guess you would have different multiple buckets for each, no, sorry, that's correct. We see that this happens 3 times, where a is 1, and then for this case, a is 3. But this is kind of the same idea of the algorithm, filling up these buckets, which are the disjoint subsets. Okay, so we kind of show that, okay, yes instance can be mapped to a game of Tetris. Now we have to go through the same, laborious thing of doing the same for the no instance. And the way we're going to do that is we're going to prove a series of lemmas that will then show that it's actually not possible. If we have a no instance of 3-partition, there's no way we can fill the Tetris game board. These lemmas are fairly straightforward. It's definitely not as hard as trying to grasp your head around the initial game board and the sequence of pieces. So the first lemma is that if we place a tetromino above H, and I'll remind you that H is this whole area here. So if instead of filling a bucket, we put it anywhere on top, it's going to be impossible to clear the game board by the end of the sequence of pieces. And the proof for this is that we know that our sequence of pieces works to clear H. We know that it does. And we have no fewer and no more pieces, so we know that every piece that's given in our sequence is going to clear H. But if we put it anywhere outside, now we're going to have a hole or something that can't be filled. So we can't fill it. So we know that we have to put pieces in the buckets, and if we don't, then the game board cannot be cleared. Additionally, if any piece that you put in the bucket creates a space within that channel that you can't fill, you also can't clear the board. Because we know that we need all these lines to be full, and if we leave a gap here, there's going to be something eventually that doesn't end up clear because we have a hole. So we need everything to be filled. Okay. Here's another lemma, is that if one of the pieces of a value, so a is 3, for example, is put in a different bucket than where we began, so if we were to not respect filling up this whole thing at once, then this next one, if we put something here and then try to decide to put something over here, it's also not going to work. And the way you have to prove this is really just through exhaustion. You kind of show, here's every single case of you to mess up my algorithm, and I'm going to show you that it's going to fail. So X's show pieces that end up getting blocked off. So we know that by the previous lemma that we can't clear it, the game board can't be cleared. If you see a number, it means, okay, well, you leave some stuff open, but the moment you put any other piece here, you're going to block off something else. So that can't work either. And these asterisks, all that they mean is that you can do this anywhere above 2. So you can put it here, but you can also screw this up by putting it higher up. So that kind of shows you every single combination of if you were to not do what I tell you, you're going to have a bad time. Kind of a similar thing, but if we put a piece that's not according to our algorithm, so instead of wrong bucket, we say wrong piece, it's also not going to work. And so you have examples for the begin piece failing, the middle failing, and then the end pieces failing. So I'm talking about these right here. If you mess up this, that, or this, it's not going to work. Okay. And we also have to say that a bucket must contain 3 values, and that the sum of these values is going to go up to t. So this becomes a little mathematical, but all we have to say is that we know that there are t plus 3 notches for every bucket. And we know that a value must be put into a single bucket by the other lemmas, and there's only one way to do this. And we just showed this in the other 2 lemmas. So there's t plus 3, and we have to put it in a single bucket, and there's only one way to do it. And we know that every value fills ai plus 1. So okay, what does that mean? Like, where are we getting this plus 1 from? Every single time we put a middle down, that's, part of A1. So if A1 equals 3, we have 1 notch filled, 2 notch filled, 3 notch filled. However, because we have to deal with these begin and end pieces, these also take up another notch. That's where the 1 comes from. So you have AI, 1, 2, 3, plus 1. And that's where that comes from. Okay, so each value fills that many notches. And we also know that the number of notches filled in a bucket is the amount of numbers you put in. So if you have AI plus 1, we are only putting 3 numbers in, so that's 3. So we know that it's going to be the size of B plus the sum of all these values put in, because that's every single notch. And we know that has to be equal to t plus 3. So remember when I told you about this kind of restriction that it's going to come up later? This is where it's coming up now. We can show that the size of B is going to be 3, because if it was any less or any larger, it's not going to respect this restriction anymore. So because of that, we know that B is 3, and therefore the sum of all these numbers is going to be equal to t. But if you remember, that's exactly what we're trying to show. We're trying to show that if you add up all these numbers in the subsets, you're going to be equal to t, which in this case is 15. So we just showed that. We know that once you fill it up to our respective method, you're going to get equal to t, which is exactly showing that, here's how we take a 3-partition problem and put it into Tetris. So this is kind of the end, right? We say that a no instance reduces to an instance of Tetris where the game board cannot be cleared. Because if we deviated in any way, you would not be able to clear the board. So therefore, a yes instance of 3-pat has to map to Tetris, yes. And an instance where 3-pat doesn't work, you will not be able to clear the game board based on the other lemmas. So that's why we took all this time to go over all these silly lemmas that built on each other to show that the no reduces to the no of Tetris. And once you do that, this is kind of the end, right? We did what we needed to do. We built the game board, we built the algorithm, we showed that yes maps to yes and no maps to no, and we reduced 3-pat to Tetris. And because of this reduction, Tetris is going to be just as hard as 3-pat is. And so because of the same hardness, we showed that since 3-pat is NP-complete, Tetris is also going to be NP-complete. So by this, we categorized the game into a complexity class and kind of built on our intuition in the beginning of saying, yeah, why are there some things that are kind of easy to check, but actually finding these algorithms is really hard? Well, we just showed why, and that's because it's in this hard complexity class. So that's the talk. I hope you guys liked it. Oh, sorry, before I, are there any questions? I'm not Zooming, I'm just recording this for myself just in case, but are there any questions about what we went over before we call it? Anything about the proof or why we did things the way we did? Yeah?
I see the definition for the NP class again.
Yes. NP, not NP complete?
I got NP.
Yes. So NP complete is just a set of the problems which we can reduce any other NP problem, y to x.
Sorry, I mean the NP.
Oh, my bad. So I guess you have it up here too. And it's a little confusing because there's different definitions for NP that are all equivalent but are all kind of saying a different thing. So this one, if you are curious, is called the verifier definition of NP because we're talking about checking things quickly. Yeah?
So is the P class class of the instances of the problems or of the general?
It's actually the problem. It's not an instance because you're able to solve it. Well, here's the thing, right? Is we know that a P problem, where did it go? We know that a P problem is also going to be an NP problem. So if we know that we can solve something quickly, we can obviously check it quickly too. So actually, every P problem is an NP problem. What we just don't know is, are these sets equivalent, or are they of different? Is P a subset? That's the big question. But we do know that P is within NP. We just don't know if the subset is strict or if it's weak. Yeah. Okay, great. Thank you so much, guys.
Thank you.